All right, so we're going to continue with the applications of the integral. This time we're not going to be computing areas, but we're going to be computing volumes. Let's start with a line. Let's say we draw a line here. Let's say that that line is going to be y equals 3 minus x. Let me move this y out of the way there. That intercept would be 3 here. Let's put y up here. And this x-intercept would be here at 3. All right, and what I'm going to do at this, I want to create a volume. Right now we don't have anything like it. We have an area, if you will, but that's that. So what I'm going to do is I'm going to attach, for example, a square at every point on this line. So a infinitely thin square. Let's change color to see if we can see it. So I'm going to go in this direction. So perpendicular to the line. And I'm just going to, well, I guess I went a little too far. Let's delete this line and redraw it. So I'm going to go ahead and attach one square at each point. So here you would have a point. Then here you want to do it more or less this size. That's not very square-like. But let's say we attach a square there, we attach a square here. So more or less this distance, that's the distance we're going to go in. That's why I did a rectangle of two times the size. The way I drew it, you have to go halfway to each, the height in each direction. I did about, you see the height here, and this is about half. This distance here I went a little too far, so really should have been the square is going to be more or less there. And you continue like that. I'm not going to draw another one because I risk absolutely butchering this picture. But you would end up with a pyramid there. And at each point you have that if you cut a cross section like this one, you would have a little square. And what I'm going to do is I'm not going to, if I wanted to approximate the volume like we did with the areas, whenever we had an area, remember what we did. If we wanted to approximate the area under the curve, we made rectangles, right? And so forth and so on. So the idea here is we're going to put a bunch of these little, not now rectangles, but you have a little volumes or parallelepipeds there that you would be adding. Oh, that made a nice design there. I don't know what that did there. So I would want to then put a bunch of those and then do a sum, take a limit as n goes to infinity and all that mess we did before. So let's pull that cross section out and try to figure out what the volume of each one of these things would be. So then we would add them and that would be our integral. So if you pull that guy out, changing color now. Then you will call this width. I cannot write it there, but I'm going to call it here dx, because I'm basically taking a cut here on the x direction or in the x-axis, and that right there would give me the thickness. So I'm basically taking this rectangle there, and so that would give me the thickness of my volume. So I want to compute the area of this. And so the area of this, what I do know is I know the height, because the height this side, I said, is going to be the same as this height right here. And that height is just the y value of the function, or of the point rather. And now the width of that is also going to be y. But y, since the point corresponds to a point on that line, is of the form 3 minus x. So the area of this, the frontal area of this volume is going to be 3 minus x squared, because it's a square. So you have base times height. Both y's are 3 minus x. So you get base times height twice, or multiply times one another is just a square of that. Okay, So now if you want the volume, then what you do is you compute the integral from 0 to 3 of this area times the width of each of this thing. This gives you the volume. So the way I would write it is that the differential in volume is just going to be, in this case, the area times dx. So when I integrate on both sides, I get that the volume, well, I want a dv, that's going to give me the volume. And when that's going to be the integral of a of x dx. And in this case, it's going to be from 0 to 3. Same here. So it's going to give me the volume from 0 to 3. All right, and so that a of x, I can plug it in now, is going to be 3 minus x squared dx. And now it's just a matter of integrating this. I use substitution. I can make u equals 3 minus x. That's probably the easiest way to do it. And it's going to give me a negative, because when I do the du, it's going to be negative dx. I'm going to avoid doing the whole calculation, but that's what you're going to get. Evaluated from 0 to 3. So when you plug 3, you notice you get 0, and then minus negative, you get minus this, in this case, minus negative becomes plus, so plus, evaluate at 0, 3 minus 0, 3 cubed divided by 3, that's going to be 3 squared, which is 9 units squared. The calculation right now I'm not too concerned with. I'm more concerned about the idea. So the idea is going to be taking a cross section, so cutting a slice of it, and then you compute the area as a function of x. You pick one x, you compute the area as a function of x, and then you multiply times your dx. You integrate between your endpoints. In this case, the endpoints are given from 0 to 3, and that gives you your volume. All right, let's do one more to see if this makes some sort of sense. Let's do it a little bit quicker for that one. Let's see if it makes sense. In this case, let's grab a line. Let's do something like this, starting at 2. And then let's do slope 1, and let's finish here at 3. I don't know. So this point right here. So the line is going to be y equals 2 plus x. It looks like a half x. That slope doesn't quite look like an x, like a 1 for the slope. But, you know, it's not drawn perfectly to scale. And now let's see if we can add cross sections that look like a semicircle. So we would have to go this distance out. That's going to be the radius. This same distance out looks about right. And we will do a semicircle here. Maybe let's dot that one because it's going to be on the inside. There, a semicircle. And then we would have to have this same line over here. It's going to be, that's pretty terrible. Let's do the way we did it. Take this distance, go about the same distance out, do a semicircle. That looked much better. Then same distance out, roughly. Semicircle again. That was not a semicircle. There, and then connect the dots. Much better. All right, so these cross sections then are going to be semicircles this time. So we're going to cut one out. So take an x. That's going to be your value of x here. And by the way, I'm going again from 0 to 3 for no reason at all, just because that's what I chose. That's going to be my x right there. You're going to take your cross section. It's going to be a semicircle. That didn't work out, huh? Let's try again. Much better. Sort of. No, I'll try again. I told you, drawing is hard. And then you take your cross section, your differential of width there, and so you're gonna have that differential there. All right, that turned out pretty decent for my drawing abilities. That is chef kiss. Okay, anyways, let's go ahead and look at that. So we pull that wedge out. And now to me, now that I see it from a little bit further, because I was zooming in my tablet. Now I look at it, it looks like a taco, but whatever. Let's keep going. So the area of this thing will depend on the radius. And by the way, the radius is true that it goes there, but it's a lot easier if you see it here when it intersects the line. So the radius of this thing, if you draw it, is going to be the same value as y. So the area of a section here would be pi r squared is the area of a circle, but you're just grabbing half, so divided by 2. So pi r squared, but now we remember that y is our radius. Moreover, we remember that y is equal to 2 plus x rather. So we say pi 2 plus x squared all over 2. All right, so that gives us an area with respect to x. All right, so now the volume, as we said, is going to be the integral from 0 to 3. Now that you have the area, you can do a of x dx, but a of x is nothing but this right here. So let's pull the pi over 2 out. That's just a constant. It's better to get it out of the way. And then 2 plus x squared dx. Now here you could do a u substitution. U equals 2 plus x. Du is dx. So this automatically, you can integrate it. It's going to be pi over 2. And it's going to be 2 plus x cubed over 3. And I'm not going to make a habit of skipping the u substitution. I'm just doing it right now due to the fact that the video I knew it was going to be a long video, and it's already a long video. So I'm trying to cut some steps. And yes, then I wasted time explaining how I cut the time. So yeah, I saved a lot of time and then I wasted. Good job. Anyway, so we plug in the value and we get that this is going to be pi over 2 times evaluating at 3 is going to be 5 cubed over 3 minus evaluating at 0. That's going to be, notice that when I evaluate at 0, don't get 0 this time. So that's important not to always assume, oh, it's going to be a 0. I should have actually taken out that 3 common factor here, the 1/3, made this a pi over 6. Oh well, now I did it. So 5 cubed is 125 minus 8, which is 2 cubed, and that's going to be what, 117 pi over 6. And that's how that works. By the way, wait a second, there's a common factor 3 here, because when you add the digits here, you have that 2 plus 7 is 9, so that's divisible by 3. So let's go ahead and not by 2 but by 3. So let's simplify that a little bit. So I get a dividing by 3, I get a 3. Then I have a 27, so that's going to be a 9, so 39 halves of pi. Okay, better. All right, so let's leave it at that for this one, and I'll see you in the next video.